class. Okay, so moving on to a new topic, we're going to talk about mirrors. And we're going to start out by talking about the simplest kind of mirror that we can, which is a plane mirror. It's probably the kind you're most familiar with. Now, talking about light, there's kind of a couple ways we can describe the propagation of light. Now, light is a wave, and typically we can describe a wave, like graphically, by defining something called a wavefront. So let's say we have a source of light, and it's sending light off in all directions. And let's pick a direction. And if we plot the electric field, look something like this. And again, this would just be at one moment in time. The entire wave is moving, so at a different instant in time it would look different, like the whole thing would just shift to the right. But let's identify some points, like right here, we have our electric field at maximum amplitude, and here, and here. So yeah, we can just mark off points where we have maximum amplitude. They occur a certain distance from the source. Now, if we look at light going in a different direction, it's going to have the maximum amplitude, kind of like at the same distances. And so if we consider light just moving in all directions, we can connect all these points where the electric fields are at the maximum amplitude. And they will form, well, I'm drawing them as circles because they're all the same distance from the source. However, they're not actually circles because this light is propagating in 3 dimensions, so it's coming out of the board as well. So what we're actually looking at here are cross sections of these spherical shells. Now, we call these wavefronts. So a wavefront is just all the points on the, just like all the points where the wave is at its maximum amplitude. So again, this would be what the wavefronts would look like. And again, this is just what they look like at one moment in time. If we let time move forward, these wavefronts are expanding outwards, and then new ones will be created, and they'll just keep going outwards as the wave keeps propagating away. So we can describe waves in terms of wavefronts. And also in terms of what we call just rays. And so these rays, we notice, are perpendicular to the wavefronts. And we consider like a ray, just like the direction this particular wave is traveling. Now, usually when we're doing, for what we're doing right now, we're going to focus mainly on these ray diagrams. But we'll kind of alternate back and forth depending on what we need at any particular moment. But we can represent the propagation of light in many cases with just this ray diagram. So, like, you can easily visualize that just like a laser pointer, basically forms a straight line. Okay, so what happens when light hits a mirror? That's the question we want to deal with now. And, we're going to start out with a flat mirror. And I'm going to draw this horizontal line here. This is a normal line, perpendicular to the mirror. Okay, so what happens to light when it hits a mirror? We know it bounces off. And we know ultimately what happens when light hits a mirror is it creates an image. Like if you look in a mirror, you see yourself. You're not really seeing yourself, you're seeing an image of yourself. But we're going to consider right now just a single point. We're going to call this the object. We'll just represent it with an O typically, but for now I'll just write out object. And it doesn't have any dimensions. We'll just consider like a small object. And light is reflecting off this object in all directions. And so what happens when it hits the mirror? Now, it turns out when light hits a mirror, it obeys the simplest law you can imagine. I'm actually going to write off to the side. So let's say a beam of light hits a mirror. It's going to bounce off. How is it going to bounce off? Well, again, we have a let's draw a normal line where the light hits the mirror, and it's going to bounce off. Let's call this the angle of incidence. And let's call that angle the angle of reflection. So we measure angles with respect to the normal direction. That's, I think, generally true when you're dealing with light reflecting off mirrors. If you see an angle, that's always measured with respect to the normal. And you might wonder why, because if that normal wasn't there, if you just have a mirror, it seems natural to define the angle between the ray and the mirror itself, but we don't do that. And the reason why, it's like, the mirror is actually a two-dimensional object, and light can come in and some angle like this. It's kind of hard to define angles because we're dealing with 3 dimensions, really. We have a plane, and then the light comes in, so it could hit with this, like say this is our x direction, that's our y. It could hit here, or it could hit here. But like this normal direction, that's just a line. So we can always have an angle between 2 lines, like the ray and the normal. And so, yeah, that's how we do that. So a rule for some object like a mirror is that the angle of incidence is equal to the angle of reflection. So very, very simple rule. Now, that's what happens when light hits a mirror. It doesn't always behave this way when light reflects off other things. Well, you could argue it does, but only if you look at it on a very small scale. So if you look at a mirror, it's a very smooth surface. But if you look at like a wall or something, if you zoom in with a microscope, it's going to be a rough surface. So it might look flat to you, but to the light that hits it, it could be a very rough surface. So if this is what you see your wall as being just this nice flat surface, and light comes in, you might think it's going to bounce straight back because it's coming in almost perpendicular, but if it hits here, it can bounce back at a significant angle. So you could argue it's still following this rule, except this angle, it's not a flat surface anymore. And so light can reflect off, even if you have a close by beam, it can go off in a completely different direction. And so rough surfaces, light scatters. Depending on where it hits, it's going to go off, and even 2 close beams can wind up going in completely different directions. So yeah, but mirrors have to be extremely smooth. You can't have a perfectly smooth surface, of course, but the imperfections are very small, like smaller than the wavelength of light. So so we can consider a mirror to be a flat surface. Now the question is, we want to know what this object is going to look like in the mirror. So we're going to start out by drawing a couple of rays. One of them, let's say it hits the mirror parallel to this normal line. What's it going to do? It's going to bounce right back. And then we're going to draw, say, a ray that hits on, just at some random point, just where I happen to draw the normal line. And so it's going to bounce back with this same angle. So these 2 angles are the same. And geometry notation, we can do that. So this ray is coming from over here. Now, you're standing on this side of the mirror, so if you look at these 2 rays, you only see what direction they're coming from. You can't see that this ray, for instance, was originally coming from over here and then it bounced. All you're seeing is a beam of light, or you're seeing a ray coming from this direction. So as far as your eye's concerned, this ray came from an object that's over here. It looks like it's coming from that direction. And this ray is coming from over in this direction. And these two meet up, and this is where the image would occur. And again, we only drew 2 rays, but you can draw as many as you want. If you have it hit here, it's a bigger angle. It's a horrible normal line, but, and again, these drawings don't always work perfectly, but, yeah, like any ray hitting the mirror, when it bounces back, if we trace these rays backwards, they're all going to meet at this point, and we call that the image point. So, kind of a simple case here with a flat mirror. Now, I want to actually erase this one. So, good to draw it once so you can see it, but I want to unclutter this graph a little bit. So, what can we say about this image point? Let's define this angle to be theta. And let's call this angle phi. And of course, this is a normal line, so just by definition, these two add up to 90 degrees. And this is a line, so this angle is phi. And that makes this angle theta. Like these two angles are both theta. So we're using this famous rule from geometry that every angle is either theta or 90 minus theta. Of course, that's not a real theorem, I just made it up. But, usually that's the way things work. And it's because we're just dealing, everything's a right angle here. So these pairs have to always add up to 90 degrees. So yeah, like, this is a right angle because we consider this ray parallel to this normal line. So these two have to, all 3 angles have to add up to 180 because it's a triangle. So this one's 90, which means these two have to add up to 90. So if one is phi, the other has to be theta. So basically we have similar triangles. And let's define this side to be h and this one to be d. We can say that tangent, they share this side. So yeah, we don't really even need to talk about tangents. Just they're similar triangles. They share a side. These angles are the same. So these two distances are the same. So let's actually call this DO and DI. So DO, that stands for object distance. So let's say DO is 1 meter. That means the object is 1 meter away from the mirror. DI would also be 1 meter away from the mirror. So we have, like if you are standing 1 meter in front of a mirror, your image will be 1 meter behind the mirror. Now, if we have an extended object, let's say we have this point is going to map over here. So like this would be object 2, this would be image 2. And again, same distance behind. And so we can call this the height of the object, and this is the height of the image. So what we've learned from looking at these ray diagrams, just from looking at the angle of incidence equals the angle of reflection, we learned that DO equals DI, and the height of the object is equal to the height of the image. And so what that means is plane mirrors don't distort images. If you have an object that's 1 meter tall, the image will also be 1 meter tall. And it'll be the same distance behind the mirror as the object is in front of the mirror. So, yeah, now curved mirrors, right, like seeing like this carnival attraction where you have this mirror that is wavy, and the image you see from that just looks crazy. So, yeah, plane mirrors, they kind of simple in a way. Say kind of simple in a way. I actually read almost an entire book that was almost entirely about like plane mirrors. That was a big part of it, just talking about mirrors. Actually, a really interesting topic. It's by a guy named Martin Gardner. He wrote a lot of math puzzles. Very interesting books. But, yeah, I mean, at least as far as we're considering here, very simple things. Now, one more thing. If you're standing over here, it's like you see all these rays coming from these directions, so they appear to come from this point. However, there's no actual light coming from this point. And so when that happens, we call this a virtual image. So we'll see later when we consider curved mirrors that you can have cases where, you know, like, say you have a mirror that looks like this, you can shine light and they're going to converge at some point. And, you know, so yeah, we can have light actually converge at a point, and that would be like a real image. But here we have to trace these rays backwards. They only appear to come from that point. That's called a virtual image. All right, I think there's just one more thing I want to talk about when it comes to plane mirrors. Well, sometimes it'd be nice to be in class because we have an actual physical example of that. But let's say we have a corner mirror. So it's a right angles. So these are two mirrors. And let's say light comes in at an angle, which I'm just going to say this angle is 41 degrees. So I'll pick not even a nice angle, just kind of a random number. 41 degrees. So it's going to bounce off here, also at 41 degrees. Here, let's say this is, yeah. So that's also 41 degrees. I don't want to write it everywhere. And let's draw another normal line where it hits. So if this is if this angle, this is also 41 degrees, which would make this angle 49 degrees. So I hope you can read that. It's kind of small. Should have probably just made the whole picture a little bit bigger. But yeah, it's like we have this line hitting, you know, these two lines are parallel because it's a right angle. So this is a normal line. So these two are parallel. So if you have a line crossing two parallel lines, I think they call them alternate interior angles. I forgot what they call these things, but yes, no, these two are equal. And because that's a right angle, these two have to add up to 90. So that's 49 degrees, which makes this one 49 degrees as well. Okay, so we had a beam of light incident like that, and it bounces off these mirrors and reflects back. Now, the thing is, these two lines are parallel to each other. So let's see how we can show that they're parallel to each other. Yeah, I guess that's kind of obvious. This has to be 49 degrees because we have a right angle. So again, these two lines are parallel. And so like these two lines are both 49 degrees above, you know, these parallel lines. And so these two are parallel to each other. So this is called a corner mirror. And again, it worked out if the angle is 41 degrees, but of course that angle is random. We could have picked any angle, and provided that we don't have some crazy angle where maybe it'll miss this other mirror entirely, but, you know, for any reasonable size mirror, you know, whatever angle we shine the light, it's going to bounce back right directly at it. So if you rotate the angle, it's still going to come directly back. It'll be a little bit offset, but yeah, it's really nice. It's called a corner mirror. One thing these are used for, yeah, we have one of these in lab on the actual campus, where it's like, it's like literally like if you take the box, like the corner of a box and just cut off the rest of the box, so you have like these intersecting planes that are all mirrored. Yeah, you can shine a light and then like a laser, and however you hit it, it's going to bounce back towards you. So one thing they use these for, they put these on like reflectors. So if like your headlights, if you know it hits a reflector, that light's going to bounce right back. Doesn't matter how you hit it. Astronauts that went to the moon, the Apollo mission, they actually left a corner mirror on the moon so we can shine light and it's going to bounce right back to us. We don't have to aim it right. As long as you can hit the mirror, it's going to bounce right back. So kind of an interesting application of plane mirrors. Okay, so I think we'll stop here talking about plane mirrors. The next topic, we're going to talk about spherical mirrors. They're curved, a bit more complicated. So we'll stop this one